Okay, thank you very much. Thanks for the invitation to speak, and congratulations to KIPAC and Roger for 10 years. And like somebody else said, several people said, let's look forward to the next 10 years. So my talk is going to focus mostly on now and the future by looking back a little bit over the last few years. So I wanted to highlight at least my selection of what I think are key results in the area of pulsars and transients, and that will lead into a discussion of like, okay, what telescopes do we need and what instrumentation do we need? So there are four areas that I want to talk about. One is preferred states and the spin and the emission of radio pulsars that John Ahrens alluded to. Then gravitational wave detection using millisecond pulsars as clocks, as has been brought up. And then these strange acronyms of RATs and FRBs, recent work on transients that are highly interesting because now we see extragalactic transients. And if there's time, I'll talk about galactic center pulsars and what kind of population is there and what one can do if you can identify, that is, discover pulsars in the galactic center and time them. Okay, so as far as discrete emission states are concerned, this is a very old topic in many ways because back in the early 70s even, people were studying effects like this where the pulsar will shut off. This is a quite ordinary pulsar. It's booming away here, then it shuts off for tens of seconds, essentially zero emission, and then it comes back. There are lots of other manifestations of this. If you look here, it's the same pulsar, but you can see color-coded in the intensity here is this sort of drift pattern. There's a quasi-periodicity buried in there. And again, people studied these things ad nauseum in the 1970s, and it kind of went down the rabbit hole in the sense that they weren't well understood. But combined with some recent results that I'll get to in a second, if you look at the sort of just the bare statistics of these things, like how long does the off state last, how long does the on state last, and it turns out there's not a well-defined duration of these things, but you can look at histograms of these durations for lots of different phenomena, and you find that they're essentially exponential. Okay, so I see that as a clue, and in fact what turns out to be a very good statistical description is that these are consistent with a first-order two-state Markov process. Okay, so what does that mean? Well, it just means you have a couple of preferred states, and there's some transition matrix that defines how the states change and what the frequency of occurrence is of each state. Those processes give you exponential state durations. They have built into them, in effect, very fast state changes, and in the case of pulsars, that's typically a spin period or less. And also, whatever this process is, the statistics are stationary over many decades of time. So I think those are clues. Some objects show 4 states or more in these phenomena. So I see 3 questions here. One is, what's defining these states? And I think it's something in the magnetosphere, that combination of field and light cylinder and currents and so forth. Maybe it's acting like a waveguide in some sense, and it's driven to choose one or more of these states. And then what triggers those state changes? John likes intrinsic triggers. I am sort of fond of thinking about extrinsic triggers, like rocks entering the magnetosphere. And then the other question is, do these transitions occur, does this phenomenon occur in all pulsars, millisecond pulsars, regular pulsars, or magnetars? And this kind of goes back to the question that Roger asked about timing precision in millisecond pulsars, and are we going to hit a wall, so to speak, because of effects like this in the attempt to detect gravitational waves. Okay, so one of the recent, semi-recent discoveries reported in 2006 was the so-called intermittent pulsar, a very ordinary pulsar that shuts off for typically 3 weeks and comes back on for a week with quite a bit of variation between those state durations. And what happens is that when the pulsar is on, you can measure the spin down rate, and so that's what these red lines here represent. You can also connect those into an average spin-down rate. And you can see that the spin-down rate changes, it's bigger when the pulsar is on, and it's bigger by about 50%. So you're changing the spin-down luminosity of the star by 50%, which in this case is about 1/10 of a solar luminosity. So you have a switch on that luminosity that takes about a second or less to change. So that's pretty dramatic, and those torque changes cause a heck of a lot of timing noise or spin noise. You can account for a lot of that in this particular pulsar by fitting for the events, but there's still extra spin noise left over. All right, so nonetheless, this object is different from the previous ones I said, or I mentioned having exponential state durations, because after 13 years of monitoring of the state changes in this object, there was this paper that came out this year, and you have highly non-exponential distributions. And so what's going on there? Well, I think another clue is the fact that these authors, Young et al., also identified a 38-day quasi-period in the durations. And that suggested to me that you have a Markov-like system, which means that you have some kind of nonlinear system that has preferred states. For the other pulsars, the transitions occur stochastically. In this case, you drive them also with a periodic forcing function. And that kind of model is called stochastic resonance. I didn't know anything about stochastic resonance until I got interested in this object, but you can simulate systems of this type and actually replicate fairly well these state duration histograms. So the overall, I guess here's some simulations of Markov processes. The top three indicate just by turning a knob, you can get whatever pattern you like statistically. The bottom three show a stochastic resonance case where it's not obvious to the eye that this switching up and down is quasi-periodic, but if you look at the power spectrum or if you look at the state duration distribution, you've got that built-in periodicity. So I think that's a major clue, and I would, the first thing I think of with 38 days is an orbit of some kind, well outside the light cylinder and perturbing the system. So the basic idea of stochastic resonance then is that you have, let's say, an effective potential with two states, and you're driving that system in such a way that you're changing the depths of those wells. And what might be doing that? Well, I think perhaps something to do with the return current activity happening out here. Perhaps it's orbiting objects, or perhaps it's instabilities in this disk, but somehow, actually, via the return current, it's affecting things all the way down to the polar cap, perhaps. I can't take it anywhere any further than that, but I think it's an interesting way of looking at all the data. All right, so I wanted to move on to the second topic, which is gravitational wave detection, and just keeping in mind the fluctuations that I was just talking about, those are something we have to worry about in the attempt to time millisecond pulsars as accurately as possible. We have to worry about whether there's some latent torque noise in those objects. So to put it in perspective, the waves that we're looking at are in the roughly nanohertz range. That is gravitational wavelengths of order a light year. And the way we will sample those gravitational waves is to monitor a collection of millisecond pulsars. I'll show you that millisecond pulsars are by many orders of magnitude the best objects for this kind of enterprise. So by monitoring them, a collection of them, you can look for a correlated effect that arises from the gravitational waves that pass through the solar system. And this can be a stochastic background, or it can be a burst, it can be a continuous wave, what have you. But it produces a correlated effect that we can exploit to rule out other things like spin noise, and also we can build up the signal-to-noise ratio by adding up appropriately those signals. Okay, so this is not a new idea. It actually derives from the mid-70s, the idea of using Doppler spacecraft tracking to measure gravitational waves. And that was adapted to the pulsar case a few years later by Steve Detweiler. And the basic idea is very simple. You have metric perturbations that change the effective path length that the pulses propagate through. So very leisurely, with these one-year period gravitational waves, you're just changing the spacing of the pulses. So very leisurely, but unfortunately very tiny. So it means you have to have a long timing program and worry a lot about the measurement errors. So there are two terms in the perturbation that we measure here. One has to do with the gravitational waves, the metric perturbations at the Earth, and the other, the metric perturbations that take place at the pulsar. So the pulsars are hundreds to thousands of light years away. So things that happen at the pulsar end of the baseline, so to speak, 1,000 years ago also affect what we measure. That kind of effect is obviously not correlated between different objects, but this term is. And so that's what we try to exploit. Okay, this is difficult. We all hear about how with LIGO you're trying to measure a deflection smaller than the size of an atomic nucleus. Things are better with pulsars in some respects. So we're talking about longer path lengths, much larger dimensionless strains, but basically we're still talking about tracking the effective position of a pulsar to much smaller than its radius, and doing that over 5 to 10 year periods as it's translating through the galaxy at hundreds of kilometers per second. So it's a tall order, but nonetheless, we're I would say, optimistic that we're going to make a detection by the end of the decade. All right, so in terms of real-world effects that can mess this up, or at least that we have to deal with, the interstellar and intergalactic plasma comes into play. Intergalactic, not so much for gravitational wave detection, but it's going to come in later in my talk. So there's a jargon alert here. DM here does not mean dark matter. It means dispersion measure. It's the integral of the electron density along the line of sight. I do remember a talk by Dennis Sciama, and long ago. He had a slide that said DM equals DM, and he was making the case that dispersion measures had something to do with annihilation of dark matter particles in the halo. But anyway, that's not what I'm talking about. So we measure this dispersion effect that you can see here, radio frequency here, time here, and that delay is what you expect from a cold plasma, like the interstellar medium. And it's typically milliseconds. It can be seconds if you're observing at lower frequencies than a gigahertz. Now, another effect that comes into play has to do with the fact that the electrons are distributed in a turbulent-like way with a wide range of length scales. So we see multipath, that is scattering of the radio waves off of small density fluctuations. And that's why we see here, in this case, a pulse that's highly asymmetric from the multipath. Luckily, that effect is very strongly frequency dependent. It goes like frequency to the -4th power. So we can go up in frequency, and that effect will disappear. There's another effect called intensity scintillation that I won't talk about, but it actually is important in pulsar surveys and in timing. Okay, just to illustrate how good millisecond pulsars are compared to other objects, I'm showing here spin period, milliseconds to 10 seconds, and then the RMS timing residual. So if you have, for all these cases, it's roughly about 5 years of data, and you account for the known knowns of spin and spin down and any orbit that the pulsar happens to be in, and you look at what's left over. What we're looking for that's left over is the gravitational waves, but there's all this other stuff like noise. And you can see here magnetars are really awful clocks. The units here are microseconds, so 10 to the 6 microseconds is also known as a second. That's awful. Your run-of-the-mill vanilla pulsar here, 10 to the 12 Gauss, 1 second. Typically a millisecond, maybe a tenth of a millisecond of RMS. Millisecond pulsars are here, microseconds, in some cases less than a tenth of a microsecond. And that's really where you need to be in order to detect gravitational waves. Okay, so the best published measurements are shown here in a paper by Demarest et al. Of this year. And this is showing data from Arecibo and the Green Bank telescope using actually the previous generation of spectrometer. By spectrometer, I simply mean we take data with multiple frequency channels and we dump those channels every microsecond or so. So it's a high data rate affair. So there are two pulsars shown here. Up here, you see all the individual measurements. It doesn't look that impressive, actually, but if you epoch average them, that is, average all the points on a given day, the weighted RMS is 30 nanoseconds over 5 years. And this second pulsar is essentially, it's the second best object in this business, and it's about 40 nanoseconds RMS. We're timing about pushing 40 pulsars now, and just to be honest, the rest of them are not nearly this good. However, some of that is due to instrumental effects that we can improve, and in fact, the current generation of spectrometers have already shown big improvement in the RMS. So what we really need is something like 50 of these kinds of objects, or at least objects with this kind of precision, in order to really, I think, make it highly probable that we will detect gravitational waves. So here's a sensitivity to the stochastic background that we would expect from in-spirals of supermassive black holes. That's the primary target signal, but we can also hope to detect individual supermassive black hole in-spirals. And also in the very last stage of the merger, there's an effect called gravitational wave memory that we can also hope to detect. But I'm only going to show this, this set of curves for the stochastic background. This curve here represents our sensitivity versus log frequency here. So it's typically, it's a couple times 10 to the minus 15 in dimensionless strain. You've got this spike here because we have no sensitivity at a 1-year period because we have to take out the Earth's orbit. And anyway, predictions, simulations of a population of these binaries gives you these blue points. So you have lots of individual binaries that add up, and you get a stochastic background. If we're lucky, 1 or 2 or 3 of those may stick up above the confusion limit of that background. We might be able to detect them individually. Okay, so how much longer do we need for detection? Well, it depends on certainly the two effects I talked about, the interstellar medium and the spin stability of pulsars. We actually choose MSPs based on their having low spin noise. A couple of them actually have detectable spin noise, so we throw them out, essentially. And as surveys continue, some of which are done by a combination of Fermi and follow-up radio, we're adding new high-quality MSPs at a rate of roughly a few per year. So after another 5 years, we expect to have 60 plus pulsars in the array, and combined with the better spectrometers, and also with the fact that with a stochastic background, the signal grows with data span as t to the 5/3 power for that stochastic background. It's a very red noise process, and so as you get a longer time series, the signal is actually growing. So we can exploit that as well. And then also the correlated Earth term grows as the square root of the number of millisecond pulsars. So you put all this together, and we have reason to be optimistic. It's plausible that we'll detect the stochastic background, but to be honest, again, whether we do or not does depend on the astrophysics of that population, for sure. Okay, great. Okay, so now third topic is transients. So when is a rat an FRB? Well, what is an RRAT? Well, it's a rotating radio transient. This is the nomenclature that was in this paper by McLaughlin et al. In 2006. These are basically individual pulses seen in the same data used in pulsar surveys looking for periodic sources, except you only see them as single dispersed pulses. And then after they're followed up, in many cases you see that they are periodic, and so that's why we say they're rotating. And for whatever reason, these are much more heavily modulated than your standard pulsar. There are a few cases where these are one-off objects. That is, like in this case, this is sort of a one-off. In the Arecibo P alpha survey, you see this one bright pulse and these two little outrigger pulses, and that's it. All the follow-ups have shown nothing. So the spacing here, I think, is about 0.7 seconds. So this is certainly plausible that it's a rotating object, but for some reason it was induced to turn on briefly, and now it's off for a long time. So these are, so people think of these as galactic because their dispersion measures can be fully accounted for by the electrons that we think are in the galaxy. So we have an electron density model, and you can account for the dispersion measures. So the FRBs basically look the same in all respects as the rats, but people are calling them FRBs. They have millisecond durations just like the rat objects, but their dispersion measures are too big to be accounted for by the galactic electrons, and too big by a lot. So so far there are four that were recently reported in a paper by Thornton et al. And then depending on your degree of belief and whether something's public or not, there are 3 more that are in the works. So here's some examples of the dispersed pulses. One of them is this burst called the Lorimer Burst, which is still a bit controversial, even though it seems to be corroborated by this recent FRB that was just published. The recent FRB has a very high dispersion measure, and it also shows this asymmetry, so that says that somewhere along the line of sight there's scattering. The authors claim that this object is at a redshift of about 0.5, but that assumes that there's no or very little contribution from the host galaxy to the electron, to the dispersion measure, and that it's our galaxy plus the IGM largely. And I think that's a very open question, but no doubt there's something along the line of sight that is causing multipath, and that's also an interesting clue. Okay, just to demonstrate that these are, it's a safe bet that these are extragalactic, I'm showing the electron density model, contours of dispersion measure, and the black contour here is 375 in these units, and that's the DM of the FRB that has the lowest dispersion measure. And so all these points, all 7, there are 4 here, the Lorimer one, there's 1 here. This one here labeled Keen et al. Could be galactic, so I wouldn't bet on that one, but all the others are safely extragalactic. In one case, 33 times larger number of electrons than you can account for by the galaxy. So I think there's no question that these are extragalactic. So the basic numbers are kind of astounding, though. If you take the 4 bursts that were discovered, reported recently, those are from the Parkes telescope in Australia. So 4 bursts, they surveyed 4,500 square degrees with 270 seconds dwell time. So that translates into 10,000 events per day over the whole sky. So that has gotten people kind of motivated to search for more of these things. And it's quite a bit of leveraging, to detect 4 or 7 of these and then translate it into 10 to the 4 per sky per day. But that's what we have to go with. So one of the activities that's taking place then is to put in the appropriate modes using the correlator at the VLA. So it's this big massive thing that fills a room, and it's a supercomputer, many petaflops. So what one wants to do is to localize these things on the sky so you can find counterparts. It's obvious, just like with GRBs. So you need a fast imaging mode, and that's being put in place pretty much as we speak, 5 millisecond dump times. And then if you can catch one of these, you can localize it in the images. This same correlator is going to be, we're also developing the phased array mode so that we can phase up the array and point a single beam on the galactic center and try to find pulsars in the galactic center. Okay, I'm going to have to skip some of this, and I'm going to very quickly say something about the galactic center science. We don't know about pulsars deep in the galactic center because of the multipath that arises from the dense plasma surrounding Sagittarius A star. But we have modeled that region, and if you go up to a high enough frequency, you can detect some of the ordinary pulsars. And it turns out the orbital effects, the post-Keplerian effects, perturbations from other objects like other neutron stars and black holes in that region, those effects are big enough that you can actually use the crummy timing precision of an ordinary pulsar to probe these things. And of course, those are the ones that are easiest to detect. So the name of the game is that there is a program that will, I think the best hope currently is with the VLA. Then when Meerkat, the South African square kilometer array prototype, or precursor, I think is the right word, will come online, that'll be useful. And then the square kilometer array phase 1. So I'm going to have to wrap this up pretty quickly here. So for the future, since my time is up, I have no future. The goal is to have a full galactic census, to find lots of pulsars, but especially the interesting ones, canonical pulsars, millisecond pulsars. The yellow here represents the population that we know today. It's about 2,200 pulsars using the Chinese FAST telescope plus other current telescopes, and current telescopes. And then the SKA, you can expect to find about 10,000 pulsars. And including the galactic center. So let me just say something about the next 10 years. I would characterize this field as a kind of an oxymoronic dividend-paying growth stock. The dividends are those things I haven't talked about, precision neutron star masses that were mentioned earlier. There will be lots of those that come out of the surveys for double neutron star binaries and white dwarf pulsar binaries. We will also do a much better job on modeling the Milky Way's electron density and magnetic field. The growth areas are gravitational waves, the Sagittarius A star, its locale, and then in general, time domain discovery science. So a big part of this comprises the telescopes, but also the processing that you need. So I'll finish there. Thank you.
Jim, without this work that's going on the correlator for the fast response, what's the current response, on the different, in Australia or VLA?
So more of the programmatic response.
I meant
how quickly can you respond to an alert?
What I meant is how quickly are the alerts getting out?
Oh, I think it's 20 minutes, I think is. For the VLA, I think the fastest is about 20 minutes.
Okay.
And people are very keen on this because of these extragalactic bursts and wanting to find counterparts. And the idea is to trigger other telescopes and be triggered by other telescopes.
Yes.
Could you say a little bit more about the Arecibo detected FRB? Because one of the worries has been that the only detections have been at parks.
Yeah, that's a good, and that was kind of buried in my slide. There have been what you might think are false alarms, and there's some worries about the Parkes events because there are some atmospheric events that we're seeing that are interesting in and of themselves, but not astrophysical. The 4 new ones, I think, do not suffer from that ambiguity, but nonetheless, one would hope that you'd find some of these with other telescopes. And it really boils down to how much solid angle have you sampled and with what kind of dwell time. Arecibo is the biggest aperture on the planet, so it has the smallest field of view. So even though we've put in 1,000+ hours of telescope time, much of that is looking towards the inner galaxy, and we would have a hard time separating an extragalactic burst from, because we're integrating all the way through the galaxy. But the one that we found is towards the anti-center. It's weak. It's weaker than the Parkes burst, but it's very believable. And I wasn't really supposed to talk about it, but I hear it's been leaked at another meeting that's going on simultaneously. So.